Um, while we're waiting for that to get started, da, da. Uh-oh. Okay, everyone's here. Hey, good morning, everyone. Live stream has started. My apologies about sending out the homework so late yesterday. We ended up covering different material than I expected yesterday, and so then I wanted to change the homework. Ultimately, I wasn't able to do it on time because my boss immediately had called me in for a meeting. I was actually mid shave. I didn't even have time to get my glasses or socks. I just ran out the door. And so then I had to do it later in the day. But I saw that some of you still turn in the homework or at least have done some of it. So I appreciate that. Thank you guys so much for that. Um, let's go over some of the problems, and then maybe some of the rest of that we'll assign as homework for today. Uh, there's kind of two different paths of material that we have to cover. One is just general concepts, like what are, some of these um, features in Python, what are some of these basic data structures, and then some of it is, some of these algorithms and things like that. So we got into some of that with the, all these sorting algorithms yesterday, but it's hard to practice sorting algorithms if you're not familiar with data structures. It's hard to do any interesting problems with data structures if you're not familiar with the algorithm. So um, I know that it feels like sometimes we might be learning divergent material, but I appreciate that all of you seem to be keeping up. But if you do have any questions or concerns, please let me know. Uh, let me share my screen and pull up the homework, which I had, and now I can't find. Okay. Give me a second. In the meantime, do people have any questions from their sorting algorithms yesterday? Anyone? Okay, I'm gonna assume that's a no. And so why can't I find I had the homework up? Okay, that's fine. I'll just create a copy of this file. Yeah, so one thing, there's a few things I wanted to say yesterday. One, I think Mino asked at the end, hey, what is the sorting algorithm that Python uses? And that's called timsort. And I said it's good for list, things like that. What I meant by that is it's not, I didn't mean to say it's good for sorting lists. It's good for sorting specifically when there are objects inside of the list. So if one of those objects, like the one of the elements you're sorting itself is a list, timsort is efficient for that. And timsort also harnesses some of the benefits of the fact that a lot of times you'll have lists that part of them are already pre-sorted, so it won't resort them. It'll use that and take that into account. But okay, and then also we covered I think I said insertion sort yesterday. Sorry, that was selection sort. That was the sorting algorithm you guys came up with. That was selection sort. Um, that takes about n squared operations we said, right? If there's n elements, there's n times we have to go through the list and n times we have to potentially make swaps or something like that, or comparisons. We'll learn insertion sort today, which is a bit more efficient. Well, first let's cover some of these problems from the homework. So what does this function do? Mystery function a comma b. I wanted to assign this problem because the idea is just to be able to go through code, and even if it's a little confusing what it's doing, figure out strategies that work for you, whether it's just plugging in different inputs and seeing what you get or working through it yourself. How many of you figured out what this piece of code did? I think it's
Swaps A and B, doesn't it?
Took
yes.
me
And
way too long to figure it out. I had like five different answers because it was so odd. I've never seen a way of doing it like that.
okay, let me give
Wait,
you. Yeah,
it
go ahead.
didn't it just return A and 0?
Uh, let's see. Well, let's
No,
see
it
what it
swaps them, I
returns.
think.
So we can do this. Let's try with a lot of different inputs. Mystery 4 comma 6, mystery 2 comma 0. So what do you think it's doing just based off of me?
Oh yeah, then it's swapping them.
Yeah, swapping them. Sure. So, but if we want to be a little more um deliberate about the whole thing, I mean, we don't necessarily need to go as far as writing a mathematical proof, although that's definitely what's done for algorithms because I mean, you need to be able to prove that, oh, okay, it works and also it takes as long as I expect. So how do we figure out what this is actually doing? Well, let's just write out what the value is after each step. So right now, um, A new equals to like A original plus B original, right? And then we say B new equals to A new minus B original, which is equal to this minus this, which is equal to A original. And then finally A newer equals to A new minus B new, which is equal to A original plus B original minus A original. So this is equal to B original, right? So we return A newer and B new, so that returns B original and A original. So does that make sense how they get swapped like that? And this is like kind of maybe an efficient way to exchange the values in a situation where you don't want to create like a third variable or something like that. There's a lot of kind of tricks that exist out there, and you kind of just have to know them. But some of these tricks you'll see are like more useful than others and used more commonly than others. This probably you don't have to do unless, I don't know, we were back in the 1990s and we were running out of RAM to create new variables or something like that. Okay. So let's move on to the next one. So how do people approach this find second largest? Or if you didn't get to this, how would you approach it? How would you find the second largest element in an array? Minu, any ideas?
Yeah, what I did was that I just found the largest and then I created a new list and then dropped the largest value. And then I found the second largest basically, or the largest again.
Okay, sure. Anirudh, do you want to help me with writing the code for this, please? Or did you have a similar approach, by the way, or
Yeah, something similar. Yeah.
okay. Do you want to share how you did this?
So I didn't like finish the entire code yet, so
Okay, that's fine. But how would you get started?
so I would start off by like first probably sorting out the function. So sorting out the array so that it's completely in order.
Okay. So let's sort this array. Um, for now, let's just do the simplest thing we can, which is use the sorted uh function inside of here. And Evan's also posted an implementation. Let's go there. Give me a second. Okay, so you found the sorted list on your now what do we want to do with that?
Uh, then probably you remove the maximum value in the array.
Okay. Do we even have to remove it if you've already sorted it like this?
You can
Oh,
just do it
probably not.
like
You can just use
-2.
you could probably just yeah.
Okay, so we can return maybe the negative second element and that'll give us something. Sure. So find second largest is sorry. Okay. So we return 53, which is the second largest. This works. Manish said, hey, why don't we, just find the maximum element, do r dot remove, and that's, I think, also would mean when any of this suggested, and just return then what's the new max. Now, Evan read the instructions, and he is not relying on, I think, the built-in Python functions. So let's see what he did. So he's finding the largest, which is kind of like, using max, but he's, figuring out what the index is and the number, keeping track of that. And then he removes the element at that index and figures out what the largest remaining one is. So this works. Let's see, means thing for item in R if item is yeah, okay. So these work, yes. And we will, if not today, hopefully tomorrow, figure out though there are faster ways to solve this. So, but this is good practice for kind of if you were sorting it out yourself, or if you're writing the algorithm to actually create the maximum thing yourself, that would be good practice. So search 2D matrix. So this is, I think, indices. I want to make sure you guys understand how to use this. So Jacob, help us with this. I think this is the easiest of these problems, but how do we start from the top left and work our way down each row and then column when we're searching for some element?
Is that the one where you have to start from the top right and go down the columns, or is that the one where you go down the rows?
So, sorry, say that. Say it again.
Is that the? Oh no, that's the other one. I'll send the code for that.
Okay.
Most of it is just the comments.
This is pretty nice. Yes. Okay. So I what I really liked about the way Jacob did this is I think in the past sometimes I've seen some solutions where people kind of just look at the example and they're like, well, there's 4 rows, there's 4 columns. Let me just hard code that in. Jacob not only didn't do that, he first of all used just the len function to figure out how many rows there are. Great. Now he's not even assuming that each of these rows has the same number of columns. In this case, maybe you can because it's a 2D matrix, but like it might be good to be as general as possible. So, if for whatever reason this had 5 elements in it, like his code still works, his solution still works. And so he just said, okay, for this particular row that I'm looking at, what is the length of that? And then figuring out the number of columns there. And then he basically, just confirms, is it the target or not? And yeah, this works. Great. Okay. Now let's start with this code and then try to modify it. But we want to now search from the top right corner and work our way down each column and then each row. Okay, so any suggestions on how to do that, Evan?
You should swap I and J in the second part. And you can, so you should swap yeah, you can swap the indices. Okay, so and then
Where should I swap it? Like lines 5 and 6 or in 7 or what do you?
Yeah, you can say for I and for J. So yeah, swap the for I and for J.
Okay.
So just
So let's try. Okay, we can assume
And
that
instead,
the rows have the same number of columns. So let's do it like this. And that way, yeah, we're not relying on the value of I before we even assign it. Okay, great. So we have these first two lines. Now what?
okay. Now, what you should do is you should say, you swap out I for len of matrix, minus I plus 1. No, minus I minus 1. Minus I minus 1.
So here you're saying len matrix minus I minus 1. Is that right?
Yeah. Yeah.
Okay. Great. And then that allows us, and do we have to do anything else? Or is that it?
I think that's it, right? It goes down each column first. And then row.
Okay, let's try this out. Okay. So this definitely gives us a solution. So we want to first work our way down each column and then each row. Okay. So if we were looking for 9, we start over here and we should actually just return just that one. And so this is the correct answer. Now if we're looking for 7 here, right?
7. Okay, that's wrong.
It should be returning 1, 3, right?
Yeah.
Yes. So keep in mind, this is the rows, right? This coordinate, and then this is the columns. Now, if we're working our way down each column, right, it makes sense that what would make the most sense, I guess, is we want to be able to change basically the row coordinate, right? We want to keep the column fixed. So by changing the orders of line 5 and 6 the way you had suggested, that's good, right? We have a fixed column, add some specific value, and then we iterate through each row in there. But now the question is, how do we want to iterate through the rows? And are we doing it in the correct way? So we want to start in the top right-hand corner, right? So that means we should start in row 0 and column 3. But here we're starting in row 3 and column 0. Does that make
Okay.
So I think you probably have it now figured out, but let's see if other people can help you out and also know what's going on and how to fix this maybe. Manish? Do you know what to do? Right now, we're starting at 3 comma, sorry, we're starting at 3 comma 0 instead of 0 comma 3. What should I change, Manish?
Well, we probably have to flip the indexes then.
Okay, how do I flip the indexes? What should I write?
So it'd be matrix J and then len matrix.
Okay, so now what we've done here, this is no longer representing columns, this is representing rows, this is representing columns. Okay, so let's try this. Well, this gave me the same answer. Not only did it give me the same answer, let me show you something else. Let's say I were to add a new row here. Let's just do the same thing here. We have now, let's say, 0, 1, 2, 3, 4, right? Or basically 5 rows, right? And 4 columns, right? Here we're saying J can be anything from 0 through 3, right? It takes on the value 0, 1, 2, 3. This now in this new example, it takes on the value 0, 1, 2, 3, 4, right? But inside of here, right, you're saying that the row, right, that we index into can be anything from 0 through 3. And this column over here, right, can be anything from 0 through 4. You see the problem here? Can someone explain to me why we shouldn't swap it like this?
Well, then we're probably gonna get an index out of bounds error, right?
Exactly. So let's try, if I give you a number that's not even in the array, something like this. Well, hold on. Whoa. How did that not trigger an error? I'm surprised. Okay, let me think about it. Line of matrix minus I minus 1.
Wait, try 17. Try putting 17. That probably would get an index out of bounds, right?
Uh, or maybe I should add a extra column instead.
Unique array.
Let's try this. I Oh, I'm surprised why this isn't starting. But the point is that we're not actually searching through the element that we expect we are when we switch the column and rows, right?
Wait, so oh, so we would just return j comma I instead of I comma j, right?
Well, we
Since
could do
since
that.
since right now it's being flipped and we just have to unflip it. I think we still have to fix the if statement.
Yeah. So okay. So a couple of things. Okay. So if this though is based off the number of columns, right? And this is based off the number of rows. But then we have J being used as the index and going through every single possible. J is being used to iterate through the rows, even though it represents, which column we should be in, right? And this is being used to iterate through the column, even though it represents the row we should be in, right? So this isn't going to work. And I need to think, why is it not, triggering an out of bound error yet? I'm surprised. But let's this is length of 5. 5 minus I minus 1, 0 minus 1. It's interesting. Let's just print out J from I each one. Wait, this is my bad. I did not replace these. That's why. Okay, there we go. List index out of range. That makes sense. Okay, so does it make sense why we're getting that error? List index out of range. Does that make sense to people? We're saying, hey, there's like 4 rows or something like that, but 5. Sorry, four. Let me get rid of this, and let me just make the example simple. There's 4 rows. Sorry, there's 5 rows and 4 columns, right? But what I'm doing is I'm trying to access column 5 instead of row 5 because of the fact that I'm using J, which represents the column number I'm in. I'm using that to figure out that I'm using that to index into a row. Does that make sense? Does that make sense to people? I need yeses in the chat, or nods, or shakes, or thumbs up, or okay. I have, I think, like 1 thumbs up. I don't know if anyone else gets it besides Jacob. Yes, Evan. Okay. Minu's nodding. Manish, yes. Anirudh, yes. Okay, great. Cool. So we don't want to switch necessarily these things. And certainly, I mean, if we do swap these, right, it does make sense to swap this, but it doesn't really make sense to swap any of this right now. So let's not swap these. Let's keep this here. Okay, let's go back to what Evan had done here. Instead of having this as I, he started here. Why? Because instead of iterating from 0 through 4 in this case, right? He wanted to go from 4 to 0. He wanted to start at the bottom row and work his way up. Now, this works if we wanted to start at the bottom left and work our way through each column and then row. But we want to start from the top right and work our way down each column and then left across the row. Does that make sense? So how do I start in column 3 instead of column 0? Jacob?
You would do like the same I, or not, sorry, the same J, but then instead of going to the start of the list, you would subtract.
So you're saying this?
Like you do a negative index. Yeah.
Okay. So let's see if that works.
And then you just have regular I. You
And
should
we
have I just regularly. And
okay.
those-
So starting with I regularly, that allows us to start in the top row, right? Because we start with I equals 0, then I equals 1, then 2, then 3. Great.
Yeah.
And then if we start with negative j, let's see what happens. So it's almost there, but it's not quite there. First of all, these indices don't make sense. But also, this is not exactly doing what you expect it to be doing. So it starts by looking at negative 0. What is negative 0? It's the same thing as 0. So
I'll
it's
say 0 minus J.
0 minus j.
Yeah.
So 0
That's
minus
also why I
j. 0 minus j is the same thing as negative j, right?
You should have -1 minus J.
Yeah. So we can do negative j minus 1 because, or negative 1 minus j, because that way when j starts out with as being 0 here, that becomes -1 here. And -1 is the last element, right? When j is -1 here, this 1 here, this becomes -2. Does that make sense? Do people want me to write this out? Let's say I have an array of like 1, 4, 7, 9. If we want to start here, we need to start at position number 3 or position number -1. These are equivalent. This is 0 or -4. Right? If we're using positive indexing, that's this number on the top, right? If we're using negative indexing, it's this number on the bottom, right? And so if we want to start at the end and work our way to the left, we start at 3, then we go to 2, then we go to 1, then we go to 0. Or we start at -1, -2, -3, -4. Jacob correctly identified, like, hey, if we want to use negative indexing, we want to use something like negative j. But the thing is with negative j is 0. Sorry, negative j is going to be 0, -1, -2, -3. So it's always going to be, just 1 too big. So if we just subtract 1 from all of these, right, then that's going to give us the right indices that we want in order to start here and then work our way to the left. Does that make sense? Everyone? Okay, cool. Now, if I run this code, though, I'm still not going to get the right things. Why? Because even though this is correct, right, we start at j and we start at I, and like we use that to index into the top right. What coordinates are we ending up printing, though? We're using the original values of j and I rather than the way that we modified them to index into the array. Right, so we should probably be printing out -I minus j minus 1, right? So that we're using exactly the same coordinates that we're using to index into the array. Great. So if we say, where's the first location of 9? And remember, the way that we're searching is something like this. Here, and then here, right? So this is step 1, step 2, step 3. Okay. So if we start at 9 and we are looking for 9, that's 0, -1. Those are the coordinates. That's right. Then if we're looking for 7, it should be 1, -1. That's correct. But I will say, outside of Python, right? Outside of maybe programming languages, people aren't going to know what it means to be using negative indexing. So how do you fix the indices so that it makes more sense in a kind of like a human context? How do you make it positive indices that we print out?
You can multiply it by -1.
Multiplied by -1. So I should make it j plus 1?
No, I mean like when you're returning it, you could just have like whatever is in the second slot just be multiplied by -1.
Yeah. So I'm saying I'm not gonna change the way I'm indexing, but what I return, you're saying should be j plus 1.
Yeah, I guess.
Well, 0, 1, that's 4, right? 1, 1 is 5. So
Just
what let me map this out. So basically what we're saying is, okay, so j is 0, 1, 2, 3, right? In order to do negative indexing, I need to make this negative.
the length of matrix.
Wait, sorry. Hold on a minute, 1 second. So 0, 1, 2, 3, -1, -2, -3, -4, right? So this is what j is. This is how we index using j, using negative indexing. So let's just call this neg index. I hate this, but hope you guys can see this. This is negative indexing. And then what we want to return though is the actual index. So we're -1 is really 3, right? If we're using positive indexing. This is really 2 if we're using positive indexing. This is 1. This is 0. Does that make sense? So we're iterating through j's by going from 0 to 3, right? Just because we need some counter variable, but the true index is -1 if we're using negative indexing, or 3 if we're using positive indexing. So how do I have the negative index here, right? How do I get the positive index? And I know Evan knows this, but anyone else? People almost seem scared to answer. I don't know if it's because we're not sure or just don't want to answer. Minu?
I mean, I didn't really know until Evan said it in the chat. So,
Okay. Do you get what he said and why he said it?
yeah.
I don't get it. I'm not gonna lie.
You got it?
I
Yeah.
don't get it.
Okay. Does it make sense to you how we have kind of like 3 different frames of reference right now, or like 3 different kind of number systems going on for J? So what is J
Yeah,
actually representing here? It's just a counter variable. So it's saying, hey, the 0th place we want to go, like, okay, so J goes from 0 to 3, right? Because there's like 4 different values that we want for our column. Now, J is not actually though the column number that we want to go into, right? The column number that we want to go into to start with isn't 0, it's -1, or it's 3, depending on if you're using negative indexing or positive indexing. Okay? The way though that we get from 0 to -1, right? If we want to use negative indexing, the way that we can get from J to using the actual negative index that we need is just -J minus 1. You guys get that? And if I want to print out the positive index though, the way that I get from 0 to 3, or from 1 to 2, or from 2 to 1, 3 to 0, right? If you notice, this is just, 3 minus j, right? This positive index is just 3 minus j. Now, what is 3? Is 3 a magic number I can hard code? No, it comes from the total number of columns, right? Which is 4 minus 1. Does that make sense? And the reason why we have to do -1 is because if I were just to do len of matrix 0, which is the total number of columns, minus j, the problem with this is that if I like this would start at 4, right? And so minus j gives me -0, right? Because j starts at 0. So the largest value I could get for this is 4, which doesn't make sense with 0 indexing, right? So and the largest value for j is 3, right? So 4 minus 3 is 1, right? So this ends at 1. So it goes from 4 to 1. What I want is for it to go from 3 to 0. So in order to get this to be something that makes sense with 0 indexing, we have to subtract 1. Does that make sense? Okay. And so we start out, we print out 0, 3, and then we print 1, 3, and then we're good. Okay. So let's see, Jacob's answer kind of works. So okay, so Jacob, the only I think issue that I have with your thing is just, 1 minus I, or sorry, -1 minus I is what you need instead of 0 minus I. Otherwise it works. It's just that you're printing out negative indices if you were to return location. I'm just trying to make the problem a little more complicated by saying, hey, return positive indices. And then Anirudh, you have, let's see, you're iterating through the lambda matrix, the cold
I
one.
think mine goes, rows then columns, I think.
Okay. But
Yeah.
what you did that may make it easier for people, and I would say, I mean, like, okay, you didn't use the range function. You kind of just did a counter on your own. But what you did that might have made it easier for other people as well is what we could have done for J, instead of doing all of this fancy negative indexing, positive indexing stuff, we can just say, hey, okay, let's start at len matrix 0 minus 1, right? So we want to start off at 3, right? Because len matrix 0 is 4 and then -1 is 3, because that's the index of the last column using 0 indexing, right? And then we want to stop at 0, but remember, the bounds for range, it's not inclusive of the last number. So I actually have to say -1 so that it stops at 0, right? And then if you remember, the step variable is the step parameter is the last parameter the range function can take in. It doesn't have to be a positive number. We can say -1. So it works our way down from 3, subtracts 1 each time, 2, then 1, then 0, and then it'll stop there. Does that make sense? And then I have a positive number for J being used the whole time, right? And it's decrementing itself correctly. So I can print out what J comma I looks like each time as we iterate through the array. So it starts out, wait, did I switch this? Sorry, yeah, print out I comma J. Okay. It starts out at 0 comma 3. Then it works its way down to the next row, 1 comma 3, right? 2 comma 3, 3 comma 3, 4 comma 3. Then 0, 2. Does that make sense how this works? Okay. So these are equivalent solutions. However, I would say, I like to think of, I like to do all my indexing math in one place, and I don't want to have to think about it more than necessary. So the fact that we're doing negative indexing here and positive indexing here, that makes it a little complicated, right? It might be better if we just were to use the positive index in both places so that we're not, having to think about 2 different frames of coordinates. Or it might be better if we just, start off by iterating through J in the correct manner in the first place, and it goes from 3 to 0. And then I can just use J directly. Does this make sense? Yeah, okay. I don't know. I think some of the rest are doable, but honestly, I should have made this selection sort because I gave you guys selection sort in class. That's my bad. But let's go through insertion sort now. And if you guys have any more questions about sorting algorithms, we can go through them. But yeah, let's just make sure that insertion sort we covered correctly. So let me share my screen. Start. Sorry about that. Okay. So yesterday we did selection sort. Selection sort, the whole idea was, yeah, you find the smallest one, then you find the next smallest one, then the third smallest one. That works. It's also incredibly slow. Incredibly slow in the sense that, like, hey, if your list was already sorted and like you're still going through the whole process kind of unnecessarily, but that's fine. So insertion sort though will be a bit faster if your list is already sorted. So the way that insertion sort works is let's take some numbers like 2, 6, 4, 5, 7. Let's say this is our array. Okay. So what we want to do is first, let's start by sorting the first element and make sure that it's the smallest amongst the first element, if that makes sense. So basically, there's nothing to be done really here, right? For step 1. I'm just doing it just to illustrate the whole pattern and make sure it's complete. So right now the only subarray we're considering is of the, when I say first element, I really mean, element with index 0, right? So that's this 2. Okay, there's nothing really to sort there. It's sorted. Great. Now I'll expand and see the full subarray of 2, 6. So like 2 elements now are in this subarray. Is this sorted? Yeah, it is. So there's nothing to be done. Now let's look at the next subarray, 2, 6, 4. Yeah, that's it. Is there anything to be sorted here? Yes, 4 is smaller than 6. So what we do is we'll keep moving 4 down until it reaches the proper position. So let's say 2, then 4, then 6. Great. Okay. Now let's look at 2, 4, 6, 5. So this subarray we want to look at is now 2, 4, 6, 5. Again, it's not sorted. We see 5 is smaller than 6. So we move 5 down until it's sorted. So this is sorted now. Great. And then now we look at the full subarray 2, 4, 5, 6, 7. So I keep saying full subarray. What I mean by that is we're looking at a subarray first of length 1, then length 2, length 3, length 4, and length 5. And this is actually looking at the full array now, but and it's sorted because 7 is greater than 6. So what are we doing here? Why is this faster? We're sorting parts of the list step by step. And then once it's sorted, we know that at least within that first part of the list, things are sorted. So now it's easier for me to take a new element and kind of add that to my already sorted part of the list. Because, for example, here at this step 7, right, I don't have to compare it to each of 2, 4, 5, 6 to figure out where it goes. I just have to compare it to 6. And since it's larger than 6, and I already know 2, 4, 5, 6 is sorted, I know that everything to the left of 6 is smaller. So 7 just needs to go to the right of 6. Does that make sense how it's a little faster here? There's fewer comparisons that need to be made. Okay, I mean, let's try this with a harder example maybe. So let's put 1 here, 5, 4, 3, 2, 1. Okay, great. So let's start with 5. Nothing to sort here. Okay, now let's start with 5 and 4. Or let's continue on to 5 and 4, and then we know 4 is larger than 5, so we swap it and we move it 1 spot down. Okay, now this is good. So we look at 4, 5, 3. Again, we know 3 is out of place, so we'll move it 1 spot down. So it's 4, 3, 5, 2, 1. We see 3 is still out of place, so we move it down another spot. 3, 4, 5, 2, 1. Okay. Now it's fully sorted, the first 3 elements. We do the same thing with the next element. So 3, 4, 5, 2, 1. We want to look at all 4 of those. We move 2 down. We just need to move 2 down again. And we move 2 down again. And it's sorted. Does this make sense? So now the first 4 elements are sorted, and finally we do the same thing with 1. And we keep moving 1 down until it's fully sorted. And now we've looked at all 5 elements, and so it's sorted. Does this make sense? Okay, so now we're going to implement this in code. It's not that painful. Actually, most of these things are fairly simple, but I wanted to just share this image from Wikipedia, which has a nice kind of image of insertion sort. So you start out with the list like this. The length of each bar is kind of just representing the size of the element, right? And you can see that like the first section of this array is being sorted. And then as we continue through the array, more and more of this array gets sorted. But basically, we're just adding 1 successive element to the sorted part of the array at each time. Make sense? Cool. And then it's fully sorted now. So let's write it ourselves. Where were we writing our sorting algorithm yesterday? Shoot. Here. Let me. Okay. So I actually already wrote it. Let me get rid of that. So let's say we take an array and we want to iterate through each of the values of it, right? So, but what we really care about is kind of the indices, because that tells us like what part of the subarray we are looking at right now, right? So if I starts at 0, then we're only looking at the 0th element. If I changes to 1, now we're looking at the 0th element and the element at index 1, right? So let's use this, because I don't care about the specific values themselves. I care about the indices first, right? The indices is what's helpful to me. And so now as I increases, basically I want to look at the like newest element that we're adding to this subarray that we've already sorted, right? So that's newest element is always going to be the last element in this now new subarray that we've created. So let's set this newest element j, the index of that, equal to I. And so we want to make sure j is sorted in the correct place with relation to the rest of the array that came before it. So we need to keep moving j as long as it's greater than the value before it, and as long as it's not already at the end of the list. So that sounds like a while loop to me, right? You needed some kind of while condition. So you'll do while j is greater than 0, and the element preceding this jth element is greater than it. We want to swap. All right, and then we'll subtract 1 from j each time. Because we've made a swap. Right. And when we no longer have to make swaps, that means j is already sorted. So then we can move on to the next iteration of the for loop. And then after all of this is done, we just return the array. And so let's test this out on a not at all sorted array. So 7, 3, 4, 6, 2, something like that. And that did not work. Oh no. What did I do here? Let's see. I don't know. 2, 3. How did that happen? 2, 3, 4, 6, 7. Does anyone see what's wrong in here? Okay, is greater than 0. Oh, sorry. This is not I, it's one. Got it. Okay, 2, 3, 4, 6, 7. Okay, does this make sense to people? Okay, it seems that a lot of people are already like turned their cameras off, so I don't know if people are taking naps or something, but maybe that means we should take a break. Let's take a break until 8 a.m. Pacific. What up? What up? Where is everyone at? Evan's here. I think Evan, you're the only person here. Okay, Manish is here. Where's everyone else at? Okay, cool. Everyone's here. Great. Okay, so I just wanted to revise some of the data structures, things that we did the past few days, and then we'll move on to new material. If I can find, okay, great. So I mean, we kind of already been through this, but basically the idea of programming is that you're specifying certain instructions to a computer to perform specific tasks, right? The computer is not a person. It's not going to know, like, if I say, hey, make a peanut butter jelly sandwich, put peanut butter on one end of a slice of bread, put jelly on the one end of the other slice of bread, and then put them together, right? It's not going to know, like, how to put them together, right? It's not going to necessarily put the peanut butter and the jelly on the sides facing each other, right? You might have them on the sides that are outside, you see what I'm saying? Like, so you have to really explain each and everything to the computer and make sure you've explained all the edge conditions and not allowed anything up to chance. So there's different ways in which to do this. There's different programming language styles. I'll go through that in a bit, but the idea is like, first, you need to understand the basics, right? Integers, strings, booleans, these are available in pretty much any programming language. Variable names are, hard to get right, but yeah, there's a famous joke about how there's only two hard problems in computer science. Cache invalidation, which is this weird thing with memory, and then naming variables. Because even like experienced computer scientists struggle with figuring out how to name variables in meaningful ways, while also keeping them somewhat brief. And then there's different kinds of errors that you can run into: syntax errors, runtime errors, logic errors. So syntax errors are basically they're just clearly a mistake, like, trying to use equals equals instead of equals, and then sometimes that will just prevent Python from even running it. Then runtime errors are when that's not an error that can necessarily be caught ahead of time easily, but basically something happens where, for example, you might end up dividing by 0, and then you'll throw an error while running. That can be kind of devastating in like the work environment, because of the fact that it's very if you're selling software and then like it just breaks while people are using it, that's not good, right? And then logic errors are just your code may be working but not in the way that you intended because you just made a mistake with programming. And there's different kinds of debugging tools. For Python, they're not as convenient, but the most important thing to do is kind of like understand error messages. And print debugging is a common technique that's used, where basically you just add print statements to understand what's going on as you go through your code and kind of figure out like, okay, this chunk is right, this chunk is as I expected, and you just test things incrementally. And you might also write tests for your code as you go along. So there's four more main styles of programming: object-oriented, functional, programming, and imperative. Object-oriented programming is this is maybe not a popular opinion if you were to search this up on the web nowadays, but it's a true opinion. It's the best style of programming there is. And we'll go through what object-oriented programming is in a bit, but essentially the idea is you make objects. Objects are these kind of like reusable classes with parts of code that you want to call over and over again. So for example, let's say you're making a bank, you're making software for a bank, and then you might want to create like a bank account class. And that way, if I want to create a bank account for myself, I just create an object for myself. And then I can just create a duplicate of that object for Jacob, and then for Minu, Anirudh, Evan, Manish, right? Like I don't have to recode everything from scratch. I can just reuse that object. It's the best way of programming, generally speaking, because like 99.7% of like software in the professional world is object oriented. But there are other styles. So there's kind of like a procedural, which is I don't know, imagine you're telling a robot, hey, do this, then do that, right? That kind of thing. Then there's functional, which is it's basically like, think of mathematical functions if they were code. people who are very theoretical, they love it and they're like, oh, it's so beautiful. But then the moment you want to do anything that involves input or output, it's really hard. And then finally there's imperative, which is basically I tell the code, hey, this is the answer I want. I don't really care how you do it. So oftentimes when you query a database, it's done in an imperative language because you're just saying, hey, just give me an answer. I want this kind of table, this kind of information. Figure out what the optimal way is to write it. So Python actually has a mix of all of these styles, but mostly object-oriented programming, functional, and imperative. We'll be covering object-oriented in a bit, maybe tomorrow or Monday. But let me go through this as well. Again, we've also gone through control structures, which are basically just conditional statements or if-else, things like that, where you kind of go through different sections of your code and you try to iterate only certain parts. Maybe you repeat a part until some condition succeeds. That's especially true for like while loops or for loops, right? The idea is to keep iterating until some condition is false. So let's just go through this. So for functions, we talked about this as well. Functions have parameters, also known as arguments. Different languages use different names, but like people will understand no matter what you're talking about because it doesn't really matter. Even if like officially the programming language might call it a parameter, C++ calls it an argument. People know what these means, right? So these are the variables that allow you to pass data to functions, and then there are return values that allow you to get data back. So you can have functions with no arguments. You can have functions with positional arguments or functions with arguments that you call by keyword. You can have defaults in languages like Python or C++. Maybe not so much in other languages like Golang. Functions with variable length arguments works. Functions with return values, those are important because I mean in a lot of the code that we've been doing, it was just printing out values, but we want to generally speaking return results, not just print it to the display. Yeah. And then recursion, again, we talked about this as well. We are dividing a problem into smaller, identical, similar subproblems until a base case is reached. It allows you to have something that's usually concise and elegant, as long as you can figure out what the subproblem is to divide it into, and it allows you to handle complex problems in an easier way. But it can be computationally expensive, use a lot of memory, infinite loops, excessive stack usage, right? Stack overflow errors. So this is kind of the steps we went through. You want to identify the base case and the recursive steps and ensure you progress towards the base case every time you call your function. And then you handle the base case explicitly to provide a stopping point for the recursion. So we want to make sure, for example, when we're doing the Fibonacci sequence, like we stop at, the 0th term, because if we keep calculating forever by, saying, hey, calculate the two Fibonacci numbers smaller than this, and we never have a stopping condition, it'll go forever. Right. There's the fancy, computer science terms called encapsulation and abstraction. So encapsulate is basically how do you, make a small, well-defined, self-contained function that does all the tasks it's supposed to. Oftentimes when we talk about in the context of object-oriented programming, it also means that you kind of protect the variables that, like don't need to be exposed to the public. You don't expose those. And then abstractions is kind of like, anytime you kind of make something more generalized, it's an abstraction. So the sum function, for example, will sum up any, array or tuple or set of numbers or like integers or floats, right? That's a abstraction that Python created just to make your life easier, right? Modularize and reuse. Again, these are more fancy computer science terms. Modularity just means making code reusable, and that helps it to be more maintainable and efficient to reuse. So anytime you are importing something, that library, it's called a module in Python. And that'll, hopefully if it's a well-designed library, you can use those functions, not just for very specific uses, but in more general ways. Yeah. I've talked about like, good strategies for coding, limiting function length to make it easy to understand what everything is doing. We don't really, stress this too much, but like you want to usually create comments to properly document what each function is doing. There's a lot of common jokes about programmers like returning to their code and not knowing, what's going on after like just 2 weeks. After having worked in the real world, I can see that that is not a joke. That is, in fact, completely true. A lot of my coworkers, sometimes you and me. So you want to make notes, test functions independently so that you know what's going on. And yeah, I think that's basically it. And arrays and strings, we've gone through these. There's more complex data structures that we'll actually create from scratch ourselves in a bit, but arrays and strings, just want to make sure you guys understand these. Arrays, zero index. Strings are a sequence of characters. Oftentimes they're treated as arrays of characters. And so let's see, let's go through all this, blah, blah, blah. Yeah, so a lot of string manipulation is one of three things: concatenation, right, where you're just adding two strings together; splitting a string, so you split it on like some kind of comma or something like that. So like if you have x comma y comma z, you might call the dot split method in Python and split on the comma so that you can separate it out into a list of x, y, and z. This is helpful oftentimes when you're reading in text files. A lot of programming questions for interviews, especially, just say, oh, hey, assume you have like a comma separated list of items. And so you have to split it up yourself. And then replacing. So you might want to replace one character with another character. Yeah, so we talked about a lot of these things. So 2D searching, the things that we did for Matrix, that Matrix question, right? That's useful for images, it's useful for games, it's useful for maps, databases, right? And so we'll go through some of these other things in a bit, actually, but let's not worry about that now. Let's go on to talking about Big O. So yesterday, I don't know, I think Evan was mentioning this in the chat. I don't know how many of the rest of you are familiar with Big O. Have you guys heard of this term? No. Algorithmic complexity. Okay, great. So this is new. I'm happy. I think the term Big O, it comes from O, which stands for Ordnung, which is some German word, but basically it's saying like approximately on the order of, right? So it's about figuring out relatively like kind of the order of magnitude that code is running on. But out of curiosity, before we get to this, how many of you are familiar with log? Can you put in the chat, or can you thumbs up or something like that, or say something on mute? Is there anyone here who isn't familiar with logarithms? Wait, sorry. I asked two questions back to back. One was, are you familiar or are you not familiar? Okay, wait, let me just ask, who is not familiar with logarithms? Okay, everyone knows it? Manish? Yeah? Comfortable? Okay, great. So that's good. So let's get started on this. So algorithmic complexity is also called Kolmogorov complexity. It's one of the most important concepts to evaluate the speed of an algorithm. And essentially, we're evaluating roughly how many operations code will take to run. So complexity is complicated, so let's just start with a simple example. Here's a simple line of code that, let's say I just ran it for you guys on Colab, right? So if I say print hello, it'll print hello. Now, this kind of takes a long time as far as computer time is concerned, because anytime you have an input or output operation, any IO operation, this takes a long time, right? A few microseconds, which is an eternity in computer time. And the reason why it takes so long is because you're kind of switching threads. Like, instead of running something inside of like your code, now you have to like communicate with the display, right? Think about, how much effort it must take to print something to the screen and actually change the pixels. Yeah, so that's fine. Let's ignore how long it actually takes. Let's just think about the operation. So printing, let's just say it's one operation, right? So what we want to think about is how well or how poorly does this scale? What is the asymptotic growth rate. Do people know what asymptotes are from math? Everyone? Okay, cool. So we want to see how this function grows over time. So let's say I have n people in class, right? Where n is 2, 20, or 2 billion people, right? Let's say there's 2 billion people in this class, and I print hello. Does this code take any longer to run no matter how, large n is? Is anything being executed differently? Anyone? Anyone? Bueller?
I feel like the more times you have to print it out, the longer it's going to take to run.
Yeah, but do I have to print it out more times when there's 2 billion people if I'm just printing out hello once?
No.
Oh, it doesn't matter, right? How many people are in class, right? Print hello just takes place in constant time, right? No matter what n is, it takes the same amount of computational effort to run. But now, let's say we want to run more complicated code and we're printing out the names of each person in class, right? So if I have 2 billion people as opposed to 2 people, is it going to take longer to run?
Yes. Well,
For sure, right?
it looks like all of n are the number of people in the class.
Yeah. So the number of print statements executed increases with respect to the number of people in class. So we can express how long it'll take, maybe a little more concretely. Let's say it takes like, I don't know, k operations to print a name to the screen. How long will it take to print n names? Well, if printing is, k operations, right, and we're doing each one of those operations n times, right, it'll take kn operations, right, to print out all n names. So we don't necessarily need to know even what k is, and we don't know what it is, and we haven't even defined the term operations clearly, but it takes kn operations to print out n names, right? So it's directly proportional to n. Right? We just assume it'll take k operations to print out each name, but different names actually have different lengths. So it'll probably take longer to print out my name, right, as opposed to like Evan's name or Jacob's name, right? So it's reasonable to assume that the number of operations to print is proportional to the number of characters in a name. So in that case, if it takes k operations to print, let's say, a single character, and there's k characters in each name and n names, how many operations does it take to print out each name? Well, it takes kc operations, right? Because there's, oh shoot, this would say c characters. My bad. I'm sorry. There's c characters in each name, right? Okay. So it's k operations times c characters, right? That's kc operations per name. And there's n names, so it's k times c times n operations to print out all names. Does this make sense to people? No? It doesn't make sense? What doesn't make sense?
Shouldn't it be the sum of C over all names? C varies from name to name.
No, in this example,
I guess if you say there's a mean,
like every single
I
name,
guess if you're saying like there's
every single name is the
Okay.
in this example.
okay.
Everyone go with that? Okay. But now let's change it. Let's say now there's up to n characters. Oh, sorry, up to c characters in each name, right? So my name is 9 characters long, right? Let's say everyone's, is that true for everyone in this class? I think that's true for everyone in this class. Their first name is 9 characters or less. So let's say there's up to c characters in each name, not exactly c in each name, but up to c, right? So what if every name has a different number of characters, right? We don't really know necessarily the distribution of the class. We don't know how many, names will be 9 characters, how many names will be 1 character, right? But we only care about the upper bound, right? What's the worst case scenario for how long it takes to run? So the algorithmic complexity does not change because the worst case scenario is that each name is c characters long. So it still takes k times c times n operations in the worst case scenario for us to print out every single character and every single name. Make sense? Okay, so if c is 1, it takes kn operations to print out all names. If c is 9, it takes 9 times k times n operations to print out all names. Let's say k is 1 and n is 1 million, right? Then kn is 1 million. So that means 9 times k times n is 9 million, right? this seems like a big difference, and it kind of is, right? $1 million versus $9 million. Which one would you rather have? 9 million is a lot more. So it seems like a big difference, but it seems like assuming each name takes the same amount of time. So sorry. So it seems like assuming each name takes the same amount of time to print, regardless of length, is not a good assumption, right? Because, if we were to assume all, like the taking into account the number of characters in each name is making a huge difference if there are a lot of characters in each name, right? But on the other hand, both numbers have exactly like the same order of magnitude, right? They're both in the millions, right? And we never really define exactly what an operation is. So, like, what does it really mean to say we have 9 million operations versus 1 million operation, right? If we just say that, an operation is 9 times as large as we expected, we could still say it's 1 million operations in the second case, right? So it doesn't maybe make sense. It's not really necessary for us to take into account how different all the values are for each of the lengths of the names. If we assume that the lengths of the names are relatively similar, right? If some of the names are like, 1 character long and some of the names are, 1 million characters long, though, now we have a huge discrepancy. So, what if C is about N, right? If we know that we can have up to like 8 billion names in our list and each name can be up to 8 billion characters, C definitely will make a large impact on the final value of KCN, right? So it makes sense to leave C in our equation. But for now, let's assume names are always about like 10 characters long and we can have billions of names. So then C is basically very insignificant compared to what N is, right? So we'll say that it'll take KN operations to print out all names. Make sense? So now let's say I want to put students in pairs for a group project and I want to print out all possible, pairs of students. How many operations will that take? All right. So I can do something like this, and there are n names in the first list and n names in the second list, so we have to print out n squared pairs of names. So therefore, it'll take k times n, right? Kn squared operations to print out all names. Makes sense because there's n squared pairs. But hold on, this code actually wasn't quite correct on this page, right? Because it's printing out Bagirith, or Haripra, right? It's printing out all pairs of names, including a name paired with itself, which doesn't make sense, right? I can't be in a group with myself. So let's filter this out, right? We add this if statement in, so we only print it out in some cases, right? So we only print out pairs of names where the names do not match. So this should change the algorithmic complexity, right? Instead of taking kn square operations, it'll take less. So because we're printing out n fewer pairs now. But if we print out like n squared minus n names, right? Which takes k times n squared minus n operations instead of kn squared operations, does this actually matter? Does this make a huge difference? Well, if k is 1 and n is 1 million, right? There's not really much of a difference between kn squared and k times n squared minus n, right? It doesn't matter because n squared will always scale faster than n. And we're worried about the asymptotic case, right? As n goes to like infinity or something like that. So kn squared minus n, about the same thing. Now, of course, if we were doing something like kn squared minus 1 million n, right? And comparing that to kn squared, there's a huge difference here, right? We have 1 trillion for kn squared, and we have 0 for kn squared minus 1 million n. So it seems to make a difference in this case, but what if n was like, I don't know, 10 to the power 50, right? Now even 1 million times n is not that significant in the grand scheme of things, right? Because n squared is n to the 100th power, right? So 1 million times 10 to the 50th power, that's almost nothing compared to, 10 to the 100th power. So n squared is always going to scale faster than n, no matter what the coefficient is for either of those terms. So for arbitrarily large values of n, we'll see that the impact of the n squared will outweigh the n term, so the n term doesn't really matter. And as a result, we can just drop it. So the complexity for this is equivalent to kn squared. But we weren't actually thinking about the if statement, right? It gets around n times. Let's count this as just like, or sorry, not n times, n squared times. Gosh. How do I do this? Let's count this as just like one operation for simplicity. So does this mean we have kn squared plus n squared equals to like k plus 1 n squared operations? True. Is this how we should define it? Maybe, but let's just, maybe replace k plus 1 with another variable like k2, right? Let's say this code takes k2 times n squared operations. But it's not like we had a clear definition for what k was before. And we don't know what k2 is like now, right? So we're just been simply using some kind of variable k as a placeholder. So we might as well just, instead of using k2, just continue to use k and just say, hey, yeah, it takes k n squared operations. We don't even know what an operation is, right? Like, let's just define maybe print and if as a single operation, right? Then our code just takes n squared operations or something on that order to run. So what have we learned? Algorithmic complexity is about roughly the magnitude of the number of operation it takes to run some code. So we focus on the asymptotic case. So as the number of inputs scales without bound and gets arbitrarily large when calculating algorithmic complexity, that's what we care about, right? As a result, when we add several polynomials together, like n cubed plus n squared plus n plus 1, we only care about the largest term since that will grow the fastest. So in this case, n cubed is the largest of these 4. All right, coefficients don't matter. So let's formalize this with some kind of notation. It's called big O because you usually just put O parentheses, and then kind of inside that parentheses, you write like what the order is of this function or whatever code we're running, right? How well or poorly it's scaling, right? So just printing the line hello once, for example, that's a constant operation, so that's O of 1, right? If you're printing out each name in a class of n people, that's O of n. And if you're printing out all pairs of names in a class of n people, that's O of n squared, right? So we always take it in relation to n, where n is the number of elements inside of the input, basically. But you might have multiple things that your O of n time depends on. So in our case, if we had n names, but C characters in each name, and C could be comparable to n, right? Maybe C is sometimes even larger than n. Then O times the big O time should be O of C times n, right? Something like that. So it doesn't have to be exclusively just the number n inside of here. So you can read O out loud as big O or on the order of. So O of k times n equals O of n. That's just one of the rules of big O notation, right? So coefficients that are inside of this O, right, they're just dropped by the O operator, right? So O of n, O of 2n, O of 3n, right? These all just equal O of n because they're all on the same order of magnitude when it comes to the number of operations. And again, operations is loosely defined. And then O of n squared plus n equals to O of n squared, right? If there's a sum or difference inside of O, we drop terms with less significant powers that grow more slowly. So O of n squared plus n, right? We just get rid of the n. It's important to correctly identify n in relation to what the size of the input is. So if we're sorting the elements of a list, n is the number of elements, right? If we have a program that prints out the nicknames of each person in class, n is not the number of nicknames, right? N is probably the number of people in the class because we can probably assume that each person has like a finite and relatively small number of nicknames, like up to 5 or something like that. And 5 is going to be way smaller than n as n grows, again, asymptotically. Right. So it's possible for, again, multiple numbers of similar magnitude to be part of the final value. So if we want to print out the latitude and longitude coordinates of each square mile in a city that is W miles by L miles, we would have O of WL for algorithmic complexity. Right. And so this is the kind of just a chart of how things scale and like the relative sizes of different O of n times relative to each other. So the smallest is O of 1. That's the kind of quickest algorithm. O of log n, that's the next level of quickest algorithm. Then O of n times log of n, O of n squared, O of n cubed. And, you can imagine where the other polynomials fit in. But then faster than any polynomial function is an exponential function that grows even faster. So O of 2 to the nth power, that's how we represent maybe an exponential function. And then maybe the base could change, but and then the factorial function grows even faster. It's O of n factorial is the like worst scaling kind of function. So yesterday we talked about BOGO sort, right? And the expected time, right? Not the worst case scenario, but the expected runtime for that was O of n factorial, right? Because there's n factorial different combinations of like ways to sort a list, and we just keep on randomly sorting and see, we then check if we get lucky. So it takes approximately, we expect n factorial number of times to get lucky enough to have a list in this right sorted order. Maybe after each of these times we check and see like, hey, if I multiply, after each time we sort it, right, we might check to see if the list was sorted, right? That's an extra operation, you could say. But like that's basically saying, okay, so it takes, let's say, n factorial operations to sort it and also n factorial operations to check if it's sorted, right? N factorial plus n factorial, that's 2 times n factorial, which is just still O of n factorial time. So ultimately, BOGO sort O of n factorial is the expected runtime. The worst case runtime though is infinite. I think yesterday I called that a Monte Carlo algorithm. Sorry, that's wrong. It's a Las Vegas algorithm. Las Vegas, again, another city known for gambling and casinos. Las Vegas algorithms. It's a gamble as to whether or not it'll even finish. Anyway, that's why it's a terrible sorting algorithm. So yesterday you guys came up with selection sort, right? That's O of n squared time, right? We talked about how you have to go through the list n times, and then you're making n comparisons, right? There's n passes to find like the smallest element, roughly n passes, and then in each pass you're looking at each of n elements. So that's O of n squared. Now we'll see that something like merge sort or quick sort or Tim sort, these are O of n log n, and we'll explain that maybe today or tomorrow. But is it making sense, I guess, so far what big O of notation is, and hopefully the kinds of questions I've been asking you guys to think about, like how many operations does this take, that's prepared you for this.
I don't understand, why would you use big O notation?
This is a good question, right? So basically, and maybe I skipped through the slide on this earlier, I don't know. But the idea is that like you don't exactly know how long it'll take to run my algorithm on your input, right? Like different inputs will take different lengths of time to run. I mean, maybe you could have a common benchmark, but okay, what if we're running this on different computers, right? Different CPUs, different memory systems, right? There's a lot of differences that can be there in the hardware of a computer that could impact runtime. So it doesn't necessarily make sense to compare runtime by just like taking a stopwatch and saying, hey, how long does it take to run? What we care about is how well does it scale? Because if you have a small number of inputs, right, it doesn't really matter like how long it takes. It could be a very inefficient algorithm, but it could still probably work. What really matters is, hey, can this actually work when you have like 1 million things in your list? Can you still sort it? For example, right? So this shows you how quickly an algorithm scales, or so an O of n squared algorithm is not scaling as well as an O of n log n algorithm, right? So does it make sense, like why you would need this and why this is helpful? Or like, well, I guess what were your doubts? Like, why were you thinking like, why is this actually useful? Like, what is your thoughts about that?
I just didn't really understand like the basis of it.
Okay, so
But now you explained it, I did it.
Yeah. Okay. Cool. So yeah, the idea is just and you know what, we can actually practice timing our different sorting algorithms and seeing how long each one takes. Okay. So I will say that this is algorithm theory, right? In practice, things could be different, right? So let's say we keep coefficients and other terms beside the most significant one just for now. I mean, that's not like you don't really need to for big O notation, but let's just keep the coefficients right now. So the most naive matrix multiplication that exists out there, right? If you were trying to multiply matrices by hand, this is probably what you do, right? If you want to multiply two n by n matrices, it'll take O of n cubed time. Now there's faster algorithms though, right? So one of them is on the order of like O of 1 million times n squared, right? So while in theory, the complexity of this is lower, right? Because n squared is lower than n cubed. In most scenarios, your matrices will probably be smaller than 1,000,000 rows by 1,000,000 columns. And so the naive algorithm would be a lot faster. Does that make sense? So this is kind of unrealistic to just say, hey, drop the coefficients, they don't matter. Yeah, it doesn't matter if maybe your input n is like 1 billion, if it's a billion by billion matrix. You're probably not necessarily dealing with those kinds of data sets every day unless you're like, I don't know, working for like a government lab with like one of those really, really powerful supercomputers. So you don't need something that works, on this order. O of n cubed is probably better. Right, so now let's go back to the code where we print out each pair of partners and ignore the complexity of the if statement, right? Let's say that a program checking out would just automatically ignore duplicated names. So we don't necessarily have to filter out the pair of names that just have the same name twice. Okay, so if we don't include the if statement, we would have a complexity of O of n squared. If we do have it, we would have a complexity of O of n squared minus n, because now we're printing out like n fewer items, right? So O of n squared and O of n squared minus n, they may be the same algorithmic complexity because both of them are equivalent to O of n squared, but an algorithm with the latter complexity would be faster, so we should use this approach, right? So anytime you can create a speed up in the code, even if it doesn't, actually impact the final big O time, if it's actually faster, if like, hey, I've done something that's just going to save me some work, yeah, do it, right? And while this isn't usually necessary for most problems and most competitions, if you really want to squeeze out like performance in real world tasks from your algorithms, you even have to go to the point of thinking about how blocks of memory are arranged within your computer and then write your code in a way that fetches the memory more efficiently. So this wouldn't affect your O of n time at all, since we don't care about the specifics of the internals of your computer for calculating algorithmic complexity. We just care about the algorithm. So as a result, keep in mind that O of n is a powerful tool and will usually help you to pick the best algorithm, but you have to think for yourself as to like what the most efficient approach is for your scenario. Now you can use big O of time to think about like memory, like how much, space do I have to allocate for this algorithm? Like if an algorithm is modifying an array in place, it takes, O of 1 memory. But if you have to allocate new space for an array for sorting, for example, if you're creating a completely new array that's the same size as the original one, it takes O of n time, right? And so again, you can also use O of n time to think about like, okay, how am I accessing RAM or something like that? But right now we're just focusing on the pure algorithm, right? Not anything else. It's kind of funny because some of the questions I gave you, if you remember like 2 days ago, that were from actual competitions. I looked at some of the fastest solutions that were out there, right? And there's just so much like arcane code. Basically, someone was like going in deep into the internals of the Linux system and looking through the operating system code, figuring out how the memory was arranged in different blocks. And their solution was basically 4 times as fast as what we came up with for that first like longest common subprefix problem. And that 4x speed up was just because like they knew how the memory was arranged and they were specifying and hard coding and telling like Linux exactly like, hey, put this block of memory here and stuff like that just to make it more efficient. But 21 milliseconds versus 6 milliseconds at the end of the day, it's not that big of a difference. Okay. So later we're going to learn about some data structures called maps and hash maps, actually, because we talked about hashing yesterday, right? So hash maps, right, which in Python are called dictionaries, right? They have a constant lookup time to find an item in the map, while maps have an O of n lookup time. So in C++, for example, they have what are called ordered maps and unordered maps. Unordered maps are also called hash maps, also called dictionaries in Python, right? If you want an ordered map, right, that's just kind of like a list of tuples and it maintains the order. So if you want to look up some item, right, you just have to maybe look through every single element in the list. That'll take O of n time. If you use a hash map instead, you just have to hash the key, and then that key will get hashed to like a unique value, and that unique value maybe will point to a specific position. And if it's a well-designed hash function, if it's a large enough map, there's only going to be one thing at that position. So you just have to compare what you're looking for to the item at that position, make sure it's the same thing, And if it's the same thing, great. If not, then it doesn't exist in the map. So this takes O of 1. It takes a constant lookup time, right? So our hash maps are always better than maps. If you in terms of lookup time. Any thoughts?
I mean, they can't always be better because sometimes N would just cause maps to be quicker. Yeah, I don't think they're always better.
You're right, they're not always better. And you're almost there with the explanation why. So sometimes N will be small, right? And so this will be a relatively quick lookup time. But what's important to note is basically the hash maps. How do they have a constant lookup time? Because we have this hash function that gets used. No one said anything about how complex this hash function is. Like, it could take a long time to execute, right? And so if it takes a long time to execute that hash function, whereas I'm just iterating through like a small list of n items, yeah, maps would be faster than in hash maps. And so that's exactly actually what I'm doing for some code I have to write for my job. We're processing data at like 100 gigabits per second, right? I can't be hashing constantly, right? It takes way too long to execute a hash function. Meanwhile, the map that I'm looking at, it has like 10 items in it. So if I just look at 10 items, it doesn't take that long. Or this only means that hash maps are, good to use for an unbounded number of elements. Yeah. So if n is small, the constant lookup time for a hash map is actually larger than the lookup time for a map, because it's so expensive to run a hash function in relation to just iterating through a map. Yeah. Okay. So yeah, we'll go through some code in the Colab in a bit. We'll also go through this a little more formally, but I think I want to just introduce this to you kind of on a high level. Okay, so merge sort. We went through this yesterday, right? You guys remember how that works? We split things into subarrays. Then we merged each array one by one, and we compared the elements inside of each subarray here. We merge the subarray again. Then we again combine the elements, reorder until we get to the full array. You guys remember how this worked? Okay. So the fastest sorting algorithms all work something kind of like this. So you pair up elements with n elements, right? We have over like n over 2 groups. We sort the elements within each group, then we combine 2 groups. And you keep repeating these steps of sorting and combining until you have everything. But since these subarrays are already pre-sorted, when you combine them, there's some kind of like extra information you have about these subarrays that makes it faster than to sort this newer merged array than it would be to have sorted it from scratch. Does that make sense? Do people understand why merge sort is faster than just sorting things from scratch? Yeah, because parts of the array are already sorted. Okay. So yeah, you repeat 2 and 3 until you have all the elements in one group. Right. And step 1 and 3 may take like O of n time to group all n elements together. So yeah, let's just call this O of n, right? We have n over 2 comparisons in step 2, so that's O of n. We have roughly the same comparisons when we repeat it the next time as well, right? O of n here, O of n here, right? So the question is, how many times do we repeat step 2? So we start with like n over 2 groups, then over n over 4 groups, then n over 8 groups, right? Until we get to 1 group. Right, and technically it's like you technically need to use the ceiling function to like round it up, but let's just omit this for now for simplicity, right? If n equals to 2, it would take 1 step, right? It would take 1 step until we get a fully merged array. If n equals 4, it would take 2 steps until we have a fully merged array. If n equals 8, it would take 3 steps, right? So it takes log n base 2 steps to get to like a single group, right? So this is technically like a log n base 2 ceiling function, right? But again, we can just drop the ceiling function just for simplicity. So if n is not a power of 2, just, you would just round each of these up. So it would just be, yeah, this n over 2, n over 4, right? Okay. So we're saying in each of these steps here where we have these green boxes, right? It takes O of n or something on that order to sort the elements, right? Because there's like roughly n comparisons. If people want me to explain why there's n comparisons, right? Just look at 27 and 38 or 3 and 43, right? So there's only one comparison being made here. right? One comparison, one comparison, one comparison, right? And there's n over 2 groups. So there's n over 2 comparisons being made total, right? Then here there's like n over 4 groups, but there's up to 2 comparisons being made in each of those groups, right? We have to compare the first pointer, the pointer to the like starting index for each of these subarrays, 3 and 38 first. Then we move on and maybe we would compare 27 and 38, right? And yeah, then you're done, kind of. So there's only 2 comparisons. There's n over 4 groups. So again, it takes like n over 2 comparisons maximum on this level. So there's n over 2 comparisons at each level, right? Or that's basically O of n comparisons at each level. And now we're saying there's how many levels? Well, there's or how many steps? There's log n base 2, right? So log n basically. Right. So we repeat each of these n over 2 comparisons log of n times. So this gives us O of n times log n, or O n log n. That's how long these green steps take, right? And yeah, it takes time to split this up, but like that's something like O of n time. So O of n log n plus O of n time, well, which one scales faster? N log n is larger than n, right? So O of n log n is all that matters. So the quickest sorting algorithm should run in O and n log n. Now we should think about like how long does bubble sort take, right? And how do we figure out like how long does bubble sort take? Well, we should think about like the worst case scenario, right? Maybe like a list sorted in reverse, right? Think about how long each iteration takes and how many things we have to compare. So if you guys remember bubble sort, how did that work? We basically just
You just go through and like each one you like if you find it but it's like a smaller value than the ones around it, you have it bubble down.
exactly right. So let's say we had, I don't know, 4, 3, 2, 1. Right, this would get bubbled down, so it gets 3, 4, and then 2, 1, and then we move on to 4 and 2 maybe. In 2 and 4 we can compare, right? Maybe 2 gets bubbled down, right? So maybe it's 3, 2, 4, and then 1, and then again the 1 gets bubbled down, so it's 3, 2, 1, 4. Okay, so yeah, so how many iterations could we have in the worst case scenario in relation to like if you have n elements, how many iterations might this take? How many steps? Any thoughts on this? Or let's even make it simpler. First of all, how many where this is one pass, right? Or one iteration, right? How many steps are there in this one single iteration? How many elements are we comparing? How many pairs of
And
elements?
elements, so 4 elements.
Yeah, basically, yeah. In this case,
N minus 1 pairs. N minus.
yeah, it's n minus 1, right? But the minus 1 again doesn't really matter in the grand scheme of things compared to n. So for accuracy, yes, n minus 1, 4 minus 1, right? 3 pairs. But that's basically n. That's basically 4, right? So that's so well, okay. For 4, maybe 4 and 3 are there's a giant difference. But if we had like a million elements, right, and we're making 999,999 comparisons, you can say that's basically a million, right? So yes, so there's n steps in a single iteration, right? And how many elements? I mean, the final list should look something like 1, 2, 3, 4, right? If we're sorted, and at the end of one iteration, it looks like 3, 2, 1, 4. So how many elements did we sort correctly after one step? How many elements are in the final position? I think Manish may know the answer to this.
1 or not. I guess Manish is gonna answer.
Well, no, one of them is 2. 2 is in the right spot, and 4 is.
Sure, 2 is okay. 2 is
I guess
the right place. That is true.
Yeah, it's just 2 and
also.
well,
2 and
I
4.
can't see the bottom.
It's gonna move
On
in
the
the
screen.
next.
Let me make this larger actually. Okay. In fact, let me also make it more elements. So we'll start out, let's say 5, 4, 3, 2, 1. Okay. After one complete iteration.
It still would be in the right spot, but it's gonna move.
Okay, this is like after one complete iteration, right? what we want it to look like after we're done with all the iterations is 1, 2, 3, 4, 5. Okay. So how many numbers, elements did we sort correctly in this one iteration?
1.
1, right. And so if we're sorting, let's say, only one number correctly per iteration, for the final iteration, we'll sort 2 numbers correctly. But then we also have to do one extra iteration just to make sure nothing else is gonna get swapped places or something like that, right? So, but let's say there's usually like one only number being sorted per iteration in the worst case scenario, right? How many iterations will it take to sort this whole list from 5, 4, 3, 2, 1 to 1, 2, 3, 4, 5? How many iterations will this take?
Right. Oh, it's 5 because you need one for checking.
Yeah. So 5, right? Which and if we say n is equal to 5, then how much of it? How much is 5 in terms of n, basically? How much is this number in terms of n? And that's open to anybody. It can be Evan. It can be anybody. Does it make sense why Evan said it takes 5 iterations to sort everything properly? Right.
Yeah, because it's n-1 to sort everything out, and then another iteration to make sure everything's good.
Yeah, good. Okay. And then n-1 plus 1 is just what? What is it?
It's just n.
It's just n, right? So this takes n iterations, right? So Evan said 5 iterations for this specific case where n is 5, right? But in the generalized case, if we have like n numbers, right, it could take up to n iterations. So we have n iterations, and then we also have to check during each iteration roughly n pairs of numbers, right? Maybe even if like every pair of numbers is being swapped and you want to add another step for that, maybe that's like 2n steps per iteration, right? But n steps per iteration, 2n steps per iteration. Either way, it's O of n steps per iteration, and we have n iterations. So how long will this take overall? Bubble sort. We have n iterations, and n steps per iteration. Like n passes basically, or it's, n iterations and n steps per iteration.
N squared.
N squared. Nice. Does that make sense to everyone? And I feel like Evan might have even said this in the chat yesterday, O of n squared, but yes. So O of n squared operations roughly, or maybe you said like n squared minus n or something like that, but it's basically O of n squared. Right, so it takes basically 4 iterations, right? Or 5 iterations depending on if you want an extra iteration to check everything. So this is called an adversarial case, right? You want to think of the worst case scenario someone can give your algorithm, right? And from the previous slide, you can see that only one number was sorted to the correct spot in each iteration, except for in the final iteration where we swapped the last 2 numbers and both end up in the correct spot. But let's just ignore that, right? That doesn't really matter. So if we have only have one number end up in the right place per iteration, right? It takes n iterations to sort the list completely, right? So O of n squared of time overall. Now, how does quick sort work? Right, it's similar to merge sort in that we're splitting the array in half each time, roughly speaking, and we're sorting part of it. Is there a proof? Yes, there's proofs that the best sorting algorithms run O of n log n. Could there be there could be sorting algorithms that run faster than O of n log n, but if you're thinking about the worst case scenario, no. If you don't have any prior information about your data and how it's sorted and how it's being given to you, right? Then the best you can do for a generalized sorting algorithm is O of n log n for the median case and also for the worst case. Some of these algorithms that we did actually take O of n time, like insertion sort. If everything's already sorted at the beginning, it takes O of n time. Some of these things, at least, for example, like the way I implemented quicksort yesterday, there are probably better ways. I mean, not probably. There are better ways to do it. This was just kind of an implementation of quicksort that I was trying to show. It could take a while in the worst case scenario, though, depending on how you implement it. It could take, even I think O of n squared. Merge sort, though, the way we implemented it, the best case scenario is also O of n log n. Whereas for quick sort, the best case scenario is O of n. And if you implement it cleverly, usually you can also make the worst case, not in theory, but in practice, is usually also O of n log n. So anyway, there's best case, there's median case, there's worst case scenarios. If you guys are interested in that, we can go through more of that. Maybe either later today or tomorrow. But yeah, there are proofs, and we'll prove it. Yes. Yeah. So while the worst case time may be the same, quick sort may be faster than merge sort if more of the list is already sorted. Right. So in that case, it could be as good as O of n time. Okay. So search algorithms. We went through sorting algorithms yesterday. We should talk about search algorithms a bit. Let's do this. Let's start by actually going to a Colab instead of continuing with this for now. Okay, let's say we have some array and it's not sorted. Something like this, okay? I'm looking for some element in here. How do I find this element in the quickest, what's the quickest algorithm I can write to find this element?
You would do a for loop that checks if it is or isn't the thing.
Yeah, so for I in array, if I equals num, return, well, I probably want to return the position, not just the element itself, right? So let me also teach you guys this. So there's one option would be something like doing this. Right, this works. Another option would be, are people familiar with the enumerate function? So what this will do is it'll give you an index and the value at that index. It returns a tuple when you wrap array in enumerate. So if I want to compare the value itself to num, I use val. If I want to figure out what the index is, I return index. Does that make sense? Okay. So either way, either implementation, pretty much the same thing. And if I say, hey, give me 2, it will hopefully return 4. Yes, great. So what is the O of n time for this?
Worst case scenario is that's at the very last index, so it would just be O of n.
Yes, exactly. Right. So if we were lucky, it could be O of 1, right? What's our median case scenario?
N over 2.
N
O
over
of n.
Yeah, n of 2, which is just O of n, right? Because the coefficient doesn't matter, right? O of n.
Oh,
So O of n, basically, that's how well we can do with linear search. This is algorithm, by the way, yeah, called linear search. What if the list was already sorted, though? Would that help us? How would that help us? Maybe Evan, you might be familiar with this one because this is, I feel like, a common kind of math problem. Are you familiar with the egg drop problem?
what problem?
That-
Can you repeat yourself?
Yeah, the egg drop problem. So let's say we have a building with 100 floors,
I'm not.
and you want to use the fewest eggs possible
Oh,
to check what is the
I've
highest
seen that.
floor you can drop an egg off of
Would you
without.
just choose like you would split the list in half and then you would like look at the ranges of the list and then choose the list that the number could be in and split it in half again and then do the same thing?
Yeah, exactly. So
So it just goes like log n.
yes, it would take log n steps. Beautiful. Yes. Does that make sense to people what the algorithm was that Minu proposed and how Evan got the O of n time for that? No? Okay. Let's go through this. So
Wait, it would be log 2 of n, right?
yeah, so the
Okay.
base also doesn't matter either, because if you think about it, okay, when I say log of n, I don't even care about the base necessarily. So what's my interesting is actually when computer scientists say log, what they really mean sometimes, especially in like machine learning, is ln, natural log, right? So they're kind of, instead of using implicit, a base of 10, they're using an implicit base of e. But it really doesn't matter, because if you know your log rules, right? Log of like n base 2, right, is just equal to log of n, for example, like let's say base e, divided by log of 2 base e, right? Is that right? Or is that not right? Right, and this number is just a constant, right? This number over here. So we can pull that out as a constant k, right? And say k times log of n base e, right? But we said constants don't matter, right? We don't really care about the constant. We care about just on the order of magnitude of what, something is, right? So log 2 base n, O of this is equal to O of this, O of like log n as well, or O of log en, right? Sorry, sorry for that. O. Right. So this, you can kind of drop it, right? The same thing is true, by the way, for exponentials. Like, well, let me think about this. Well, no, that's not true. That's not true for exponentials. The 2 of n and 3 of n are definitely different. I mean, we put them in the same class, like they're both exponentials, but like 3 of n definitely is, yeah, gonna scale a lot faster than 2 of n. So yes, okay. Okay, so by the way, the egg drop problem, I just love this problem, so I'm just gonna explain it. Let's say you have a building, lots of windows, lots of floors, right? There's 100 floors. You want to figure out what's the highest floor you can drop an egg off of without it breaking. And you have an unlimited number of eggs, but you want to use the fewest eggs possible, right? So you'll start at maybe like floor 50, right? And then you see if it breaks or not. If it does break, you go down to floor 25, right? You take the midpoint of floor 0 and floor 50, right? If it still breaks, you can't go down to floor 12.5. So maybe you pick 12 or you pick 13, but let's say you pick 12, right? Now it doesn't break when you drop it off of floor 12. So you use a new egg, right? You go up to maybe floor, what's halfway between 12 and 25, 37 over 2, that's like 18.5. Again, you can't go to floor 18.5, so you maybe pick floor 18, right? 18 it breaks, right? So then you go halfway between 12 and 18, so 15. 15, it doesn't break, let's say. So then you go halfway between 15 and 12, right? Does that make sense, the process, how we're doing this? So the same thing is true if you want to search for an element, right? If you know the element, if you know the list is sorted, sort of least to greatest, right? It's 2, 3, 5, 7, something like that, right? If you're looking for an element, let's just add one more element, 9, right? If you're looking for, let's say, 6 somewhere in this list, right? Let's check the midpoint. Is this greater than or less than 6? Well, it's less than 6, which means that if 6 exists in this list, it would be to the right. So we check somewhere here, right? So 7, 9, we have to pick one of these elements because we can't go into the midpoint of that. So let's just pick 9, right? Is 9 greater than 6? Yes. So then we go to the left. Now we say 7. Okay. Is 7 greater than 6? Yes, it is. So we go to the left, but oh wait, actually there's nothing left of this array now. And so we've searched all the terms, so 6 is not in this array. Does that make sense? Since we're splitting in half each time and we're cutting in half. And our base case is basically when we have an array of size 1 or size 0, right? The maximum number of steps it could take for me to possibly find a term or determine that it doesn't exist, log of n. Does that make sense? Okay, and we'll implement binary search in a bit. Let me just finish the slideshow. So it's kind of like this. Is it easier to find something in your room when something's organized or when everything's in a mess? It's probably easier when it's organized, right? Because then you kind of just go to the location where you expect it to be, right? So it helps to have a list already be sorted before searching through it for an item, and then you can use something like binary search to find the position of an item or find out if it's in the list at all. Right. So let's say we have a list with the items 2, 6, 8, 10, 12, 15, 20. Now I've ordered it into a tree. We'll learn more about trees later, and why that's helpful, but this, as you can see, like everything to the left of 10 is smaller than 10, right? Everything to the right of 10 is greater than 10. And then if you look at that, 15, everything to the left of 12, below, greater is below 15, right? Everything to the right of 15 is greater than 15, right? So binary search will cut half the items out of our search parameters every iteration. So how many iterations would it take to narrow down the entire list to one element? One element, one iteration, two elements, two iterations, four elements, three iterations, right? So it basically takes log of n operations, right, to narrow a list of n elements down to like one element, right? So you can think about this as going through each level of the tree below for each iteration of binary search. How long will it take to get through the relevant section of the entire tree, right? This depends on how many levels there are, and we'll go through trees more in depth later. But from the previous slide, you can see it's log of n, right? If we want to get to 2, right, it takes us 3 steps to get there, and there's 8, or no, there's not 8. There's 7 items in this tree, but approximately 8. So it's approximately log of n, right? Yep. So what's the algorithmic complexity of linear search? O of n, I think you guys already said, right? What's the worst case scenario when it comes to the number of elements examined, right? O of n, right? Yeah, but binary search, it's just log of n. Okay, so now let's actually implement binary search. It is a bit tricky, I will say. Well, let's just try this. Okay. So let's start with an array, and then let's say binary search. Okay. So binary search is kind of just narrowing down the bounds of each of our sorry, this should be sorted. Let me sort this, because otherwise there's no point. By the way, why wouldn't we, if we are going to do linear search, right? Why not just do binary? Let's say why not just sort the list first and then do binary search? Wouldn't that be faster? No? Why not, Manish?
Sorting.
What's the fastest sorting we can do?
Merge sort, right?
Merge sort is one of the examples of one of the fastest sorting algorithms. So, but like, what is the complexity of merge sort?
Merge sort is binary, right?
It's sorry, what do you mean? It's binary?
Wait, what do you mean by what is the complexity?
Like, what's the O of n time?
It's just log of n, right?
Is merge sort log of n, Anirudh?
Wouldn't it be like probably n log n, maybe?
N log n, right? Because there's log n levels kind of a tree that we're merging, we're going through this tree, right? And we're merging, like, first we start with one element in each list, then 2, then 4, then 8, right? And so it takes log of n steps to merge all the subarrays together. And then in each of those steps, it takes n comparisons, O of n comparisons. So it's O of n log n. So Manish, it's O of n log n to sort, right? And then it's O of log n, or sorry, and then binary search takes how long?
N squared, right?
Binary search? Remember, it's this one. Right, where we're splitting kind of the list in half each time as we go along, right? And so it takes how many steps to get there? It takes log of n steps, right? To divide it into just a list of one.
Oh yeah, yeah, it is.
Yeah. So, okay, so binary search takes log of n. Merge sort or, quick sort, these things usually take like n log n. Okay, so if we were to sort and then do binary search, what's the O of n time for that overall thing?
It's n log of n plus log of n, right?
Yes. So does the log of n matter when you just have n log n? Like which one's going to grow faster?
Just n log of n.
N log of n, yeah. So the final thing is O of n log n, right? So would it be faster to sort and then do binary search, or would it be faster to just do linear search if you're just looking for one item?
Just do linear.
Do linear probably, yeah, exactly. So that's why you might still do linear search, even though binary search is faster, because sorting does take a while. But if you have to do linear search for a lot of items, it might be more efficient to sort first, then do binary search. Or maybe use a different data structure, which we'll learn about tomorrow, Monday. But okay,
Wait, when you say log, do you mean log base 2 or log base 10?
it doesn't matter, right? Because the base can be just taken out as a coefficient, if that makes sense.
Oh yeah, you're right. Because in the fraction.
Yeah, if you remember the fraction I put up here, right? So it's like a log of n base 10, right? That's just equal to log of n, if you want to do base 2, right? Divided by log of, right? And so this number is just a constant that can be taken out because we don't care about constants. So O of log 10n is the same as O log 2n, right? So we just say O log n, right? Technically, when people say log of n in computer science, though, it's log of base en, right? I know you might probably thinking, wait, why not just use like ln of n, right? Because usually we call this the natural log in math. I don't know. Computer scientists love being different, I guess. So okay, so now let's go back to binary search though. Let's actually try implementing this, right? We're splitting the array maybe in half each time, right? So if we have an array like 2, 3, 4, 6, 7, we want to first look at 4. If it's too large, then we will look at 6 and 7. And then we'll look at maybe 6. If 6 is too small, we look at just 7. And if 7 doesn't match the element that we were looking for, then we give up and we say not found or return -1 or something like that. Okay. So binary search, let's say it should return index of element or -1 if not found. We didn't actually do that up here. We probably should have done that for linear search as well. Return -1 if it's not found. Let's just do that for completeness. Okay. So binary search, let's do that here. We need then 3 pieces of information, right? We need the original array to be passed in, right? We're probably doing this kind of recursively if you guys are thinking about this, right? This is kind of a recursion kind of problem, right? Because we're repeating the same steps over and over again. There's some self-similarity. But the array gets smaller and smaller as time goes on. We could make a copy of the array and pass it in. That seems like a lot of work though, and that's not very efficient if you think about the memory usage. So instead, we can just keep on passing in the same array into itself, but change the bounds that we're examining. So in this case, what are the bounds? Well, we'll define the leftmost bound and the rightmost bound. Okay. Okay, and what's the base case? Well, actually, let's leave that for later because it's a little complicated. And now what's the recursive case? Well, let's say we passed in an array. Okay, and let's define another function called binary search, which just kind of calls this binary search recursive function for the first time. And it defines the leftmost bound as 0, and it defines the rightmost bound as basically being the length of the array, right? So this kind of goes, beyond the edge, right? So we have to make sure not to go too far. So actually, maybe let's just make this line array -1 so that way the bounds can be inclusive. Okay, so this in this case, for this array, right, we're basically passing in the array, 0, and 4 as our bounds. Okay, great. So first we want to check the midpoint of the array, right? And check if that's equivalent to the target we're searching for. Oh yeah, that's right. We have to pass in the target we're searching for. Let's call this target. Let's pass this in target. Let's pass in target. Okay. So how do we find the midpoint of this current array that we're looking at? Anirudh?
You could probably do like array length divided by 2 and use that as the index.
Sure, but we're not necessarily always looking at the full array, right? We're looking at maybe a truncated part of the array. So how do I do this in terms of left and right?
Probably left plus right divided by 2.
Yeah. And just remember though, Python, when you do divide by 2, it gives you kind of an exact number. It gives you a float. So in order to get an integer, let's put 2 slashes and this will round down. So left plus right //2, right? If this is what we have, this is basically the new index, the midpoint index. Let's call this mid, right? Okay, now let's check if array mid equals target. If it does, then what should we do?
You would return mid.
Okay, if it doesn't, now what should we do? Manish?
Well, then we have to continue the search. So
We have to continue to
Yeah.
search. Yeah.
yeah, so that would, for that we just have to put the whole binary search algorithm, right?
Yes, we have to call it again, sure, recursively, but the question is how.
Oh, so just else
Okay.
binary search R and target.
Well, we need to pass in the bounds, right? And so the
Yeah.
question is,
Well, that
okay,
just, okay.
so let's say we're looking for the number 5, right? So if you see our number, see our example here, right? Let me move that out. Okay. If you see our example here, we're looking for the number 5. 5 is not equal to 4, right? So what side of the array should we now be exploring? Should we be exploring the left side of the array or the right side of the array?
The right side.
The right side. Okay, cool. So what should the new bounds be of the array? So before we were exploring everything from like index 0 to index 4. Now what should we explore? What can we narrow out? How can we figure out what we need to do?
Index 2 to the end of the array. So index 2 to index 4.
Index 2 to index 4. Okay, we could do that.
Or index 3 to 4.
But yes, index 3 to 4 is probably a tighter bound because we've already said that index 2 is not our number. So let's call this on index 3 to index 4. How do I do that in terms of the variables I have though? Right? What is index? So this index 2 was our mid, right?
Yeah. So our mid has to be
but what should left and right be is the question. Yeah.
Probably 3 and 4, right?
Yes, but what is it in terms of like mid and left and right, what those variables were previously? So let me actually just backtrack a second and make this a bit easier for you. So we should break this out into 2 cases, right? First of all, we should check, hey, is array mid greater than target? And then we want to check if it's less than target. Right. We want to check these three cases.
Okay.
So if array mid was smaller than the target, so as it was in this case, that example that we're seeing, right? We want to check the right-hand side of the array. So we want to check everything to the right of mid.
So
now
we'd probably do mid plus 1 and mid plus 2, right?
the mid plus 1 makes sense for left, right? Because we know we want to basically get rid of everything that's mid and to the left of mid. Right. But we want to keep everything to the right of mid, right? Is that right?
Yeah.
So in this case, mid plus 2 happens to be the last element. But you have to remember, not all elements are going, or not all arrays are going to be, of length 5, right? Let's say we have a large list of, like 1, 2, 3, 4, 5.
So it'd be mid plus 1 and then len of r minus 1.
Yeah, so if we let's say we were looking for the number 10 in this array, right? Then for example, we would check 5. Does this match? No, it doesn't. Okay, so we want to check everything to the right of 5. So that would be 6 through 9. 6 is basically just mid plus 1. And then 9, well, 9 was already the rightmost bound that we were looking at. Does that make sense?
Yeah.
So I can just pass in right here. Does that make sense?
Oh yeah, okay. So it doesn't change. I see.
Yes. So there's a few reasons why we don't want to do len array minus 1. But let me get to that actually right now. Let's not wait till later. So let's say we were looking at now. Okay, let's say we're looking actually for the number gosh, right. How do I edit this? I guess it's gone forever. Well, okay, that's fine. I'll create a new text box. Okay, so let's say instead of looking for 10, I was actually looking for the number 7.5. But in the same array as above, right? So I look at the array 6, 7, 8, 9. So first I compared 5, right? Compared 5. 5 is too small. So I look at 6, 7, 8, 9. Right, what's the midpoint here? So 7. Wait, it's not gonna work. I want 8.5, 8.5. Okay. Wait, do I want 8.5? There's no ideal solution here. Let me think. Actually, let's make this better. Let's just do 2.5. Great. Okay. So compared 5, 5 is too large. Okay, so now I'm looking at the left side of the array, 1, 2, 3, 4, right? And then I compare 2.5 to the rest of this array. And first I will look at the midpoint, which let's say in this case is 2, since I can't actually get the midpoint. So I compare it to 2. Compared 2, 2 is too small. So now I want to look at 3 and 4. Okay. So this is kind of an equivalent scenario to what you're doing right now, right? I look at the midpoint. Midpoint is too small, so I go to mid plus 1. But then I want to go from mid plus 1 to the end of the current array I'm looking at, or the current section of array I'm looking at. And since if I were to do len array minus 1, right, like you had originally suggested, then it would take me all the way to 9. And now I'm adding in all these other numbers I don't want to introduce again, right? Right is already basically the rightmost bound of the current array that I should be looking at, right? So sometimes right will be equivalent to len array minus 1, right? Which it is here because that's the initial value we passed in. But if we've already made right, if we've already truncated the size section of array that we're looking at and right is something that's smaller, we should continue using that value of right. Does that make sense? Does that make sense to everyone? Okay. So this is really helpful. And oh shoot, you said mid plus 1 and I don't know why I wrote target there. Okay, mid plus 1 to right. Does this make sense to everyone? But I still haven't or what am I doing here? Target comma mid plus 1 plus right. There you go. Okay. So now we still need the bounds for this case, this scenario, right? Where we want to look at the left hand side of the array because mid was too large. The value at mid was too large. What should I do for this, Minu?
Can you repeat the question again?
What I'm looking at the left-hand side of the array,
Mhm.
right? For this part of this if else statement, how do I look at like how do I narrow down my bounds now? What should they be? What should the new bounds be? What should left and right be here when I pass it into binary search recursive, right? For my new column.
Your new bounds would be um it's gonna be um the leftmost one.
Yeah, so we start from the left of
Yeah,
the
and then it's gonna be mid.
mid. Can we narrow it down more?
-1.
-1. We've already said mid is too
Yeah.
large to be our target. So let's just look at the section of array that's relevant to us, which is goes from left to mid -1. Okay, does this make sense to everyone how we got this recursive step? Okay, great. Now, here's the base case, right? It is possible that, ultimately we get to basically like a array of size 1, right? In that case, we'd have something like left would be 2, right would be 3. If I let that go to my recursive case, I get 2 plus 3, which is 5, / 2, which is 2.5 rounded down, so that's just 2, right? So we'd look at just element number 2 and compare that to the target, right? If that is in fact the correct element, it would return mid, which is great. Otherwise, it would make another recursive call. And then, either it will go from 2 to 2 or something like that. Wait, no, that's not right. Sorry, it would go from mid would be 2 in this case, right? So it would go from 2 to 1, right? Left would be 2, right would become 1. Or it would be mid plus 1 would be 3, and right would be 3. Right? So in this case, it's pointing to an array of 0, right? Because it's an array of from 3 to 3 is just, it's selecting 0 elements, right? We have to go from 3 to 4 if we want to select an element. And in this case, it would be selecting an array of like 2 to 1, which is just, that doesn't even make sense as far as bounds go, right? So I don't need to check for like, hey, what if, my array that I'm looking at, the section of array is now only one element, right? That one element case is handled by this part. My base case should handle the case where my bounds no longer make sense because it's pointing to an array of size 0 or even maybe of size like -1 or something like that. Right? So how do I check like, hey, it's time to finish this problem. There's no longer any elements to look for. We should just give up because obviously the element is no longer in this list. What should my base case be? Evan?
If the length of the array is 0, return -1.
Well, remember the array might be whatever length it is, right? But the section of array we're looking at is determined by left.
Sorry. If right minus left, if right minus left is -1, return -1. I don't know.
Sure.
Yeah, sorry.
That could work.
I have a quick question. Could you also do if left equals mid -1?
Where? Here in line 7?
Yeah. If left equals mid minus.
What is mid in this scenario?
If like the element you're checking is the same as like the because wouldn't that potentially mean that there's only like one item in the list if left equals mid -1?
I see. So you're saying like basically down here. So basically, if we haven't found if there's only one element in this list, and we haven't found it here, then you're saying down here we should just terminate and say something like that, right? Where left equals to mid -1. Return -1.
No. I just meant that could that condition, instead of doing right minus left equals -1, would left equals mid minus 1 also work as the base case?
Well, mid isn't defined up here, is it?
Oh, I see. Okay, okay.
So you could kind of maybe implement a base case that goes down here.
Mhm.
I wouldn't do that for a few reasons. One is like now your base case is like kind of hidden inside of your recursive case, and that's not a great style. And then we want to handle like all cases, including for like, what if we put an empty array into this and we pass that in, right? Then this would go
Yeah.
from 0 to 0, right? So already our base case should be triggered because like these are like just bounds that are just giving us an empty array. And so obviously whatever element we're looking for will not be in this empty array. So
Mhm.
while this technically works and could help you to terminate early, that saves you a little bit of memory, a little bit of stack space. If you really wanted to, you could do this. I wouldn't do this because it's I think would help make you more prone to mistakes. But this bound isn't quite right. Maybe, Minu, you can help us see, is there any other scenarios where we want to just say, hey, there's nothing in this array left to check?
Wait, could you say like if length of array is 1 and um the only value isn't the target, then return -1?
You could do that, but you don't need to handle special cases in a special manner when your generalized algorithm handles all cases, right? Does that make sense? So the general idea of recursion is kind of like you want to basically just have like a catch-all kind of way of handling and dealing with every single array. You don't want to deal with special arrays in special manners. So while you could maybe like terminate some things early, and maybe sometimes like if you're writing highly optimized code, you might do that. Like and you say like, hey, okay, honestly, there's no reason for me to do binary search when we have just like, I don't know, 5 elements. Let me just go through each one of them or something like that. You could do that, right? You could do that for just one element. But the thing is, if you have an element, sorry, if you have an array of length 1, right? Would this code still work? Yeah, it should, right? So, and it's not going to have that much overhead over just, directly dealing with an array of length 1. And if you are directly dealing with an array of length 1, now that's like an extra if condition you have to check, which could cause overhead for other cases, right? So there's always a bit of a trade-off here. And usually the trade-off is solved by saying like, okay, let's just write the simplest, most general code possible that works for all cases. And we don't have to treat special cases simply. But there is something wrong still here in this base case. There's something that, or it's not wrong. This base case is not wrong, but there is something that we're missing that we should also have. It doesn't have to be Evan who fixes it. It could be anyone. You guys know what it is, or should I give you a hint? I kind of mentioned this before, but like basically, let's say our left equals 2, right equals 3. Right. If array and then that would make our mid equal to 2, right? So if array 2 equals to 2, if our array 2 was too small, then our next call of binary search recursive, what it would do is basically it would call ESR would call array target 2 and then 2, right? And if array 2 was too large, it would
Could you maybe also just like initially just check the minimum and the maximum value, and then if that's already out of range, you can return -1. Like if your target is 5 and then um your minimum value is like 7
yeah.
when you sort it, then it's like definitely not going to be.
I see. Yeah. So this is again treating special cases.
Okay, yeah.
Treating special cases especially. What you're saying is kind of like hey, this would take me O of 1 time to like, terminate if I know like, why go through this O of log n process. And that's a good point. Maybe, yeah, we treat this case specially, right? But unless we really need to, we shouldn't, because it's better to just, again, use a generalized log n algorithm. Now, if you feel that like a lot of times for whatever scenario in the specific thing you're handling, like you're going to have a lot of things that just won't be in your list because they're too small or too large, yeah, you should probably add that as a special case. But unless we have any special information, we don't need a special case for that. But take a look at this, okay? So let's say our array or target, whatever they are, it doesn't matter. But left is 2, right is 3, okay? So then that makes mid being B2. So we try looking at array 2, and we see that it's too small. In that case, this is what we call, right? And so this is actually this, then when we call this would trigger the base case, and we return -1 because it's not fun. But what if array 2 is too large? Then we add 1 to mid, right? That's 3. And then we right is mid. So 3 to 3. And we're looking at this empty array, basically, right? Because if I try looking at, let's go here. Right. If I say, hey, print out array 3 to 3, I've selected 0 elements, right? Everyone understand why this selects 0 elements? Okay. So then if I've selected 0 elements, that should be part of my base case as well, no? Do people understand or agree or no? Anyone understand what I'm saying? Am I speaking Greek?
Why would it? How would it be part of your base case?
Well, it's not right now, but it should be, right? Like I should realize that, hey, if I'm still searching for an array, for a target in an array that's and the window of the array that I'm looking at is empty, right? It's not actually containing elements. Well, I'm done, right? Like there's nothing left I can search for, so I should just terminate, right? Return -1.
Oh, so you could say like if right minus left is -1, or if r left right, or if r left until right,
Or sorry, what?
like r, like ARR, and then the brackets, and then left colon right.
Mhm.
Uh, wait, no, sorry, I meant sorry. If left is equal to right, then
Yeah, so you can say is the length of this equal to 0, or you can just use the arrays you can use the bounds directly and just say, hey, is left equals right, right?
Wait, can you just replace all of that with right minus left is less than equal to 0?
Exactly, yeah. So this can also be right minus left equals 0, or then you can just combine these and say, hey, less than equal to 0, right? And this is always safer if you have like a less than or equal to, because even if somehow you get like right minus left becoming -2, maybe there's like an unanticipated case that came up, right? Well, it's already handled and we return -1. So any case that's nonsense, anytime we have like an empty array or something that's an array of size -1 somehow, right? Or -2 or negative infinity, right? This is always handled and return -1. Does this make sense how this works? It's been a long while since we took a break, so let's take a break till line 45 and then we'll test this out. Hey, everyone. I guess it's not yet 9:40. Okay, now it's 9:45. Hi, everyone. Is Mina there? And none of you is? I'm muted? I'm not muted. Okay. What is the other people? Okay. I'm just adding some print statements so we can understand better what's going on in this code. Okay. Do people have any questions on the binary search algorithm? Okay.
I have a question.
Yeah.
So when we're defining right and left, like say we got the array down to 6,
Mhm.
and like we're trying to see if 6 is the target or not.
Mhm.
Wouldn't left be equal to right as we're going in to check it? So then it would automatically terminate before checking if it's the target.
So let me draw this out. Let me not draw this. Right. Okay. 3, 4, 5, 6, 7. Let's say this is our array. Okay. So technically, if we're looking at just something like, if we want to say what's the specific index of each element, right? This is 0, this is 1, this is 2, right? Something like that, right? But that's only if you're extracting a specific element. So if I'm saying array 0, that's equal to 3, right? Array 2, that's equal to 4. But if I want to take slices, if I want to say like something from this index to this index, if I'm taking a range, now it's slightly different. And the way that we should think about it is this. So let's say we have 3, 4. Actually, let me use letters. A, B, C, D, right? Okay. So if I number the in-between gaps, right? So this is 0, this is 1, this is 2, this is 3, this is 4. The only way I would end up with an array of just A is if I'm taking array from 0 to 1, right? So it would be 0:1, right? That would be A. Does that make sense? And so the only way I would end up with like just 6 is, in this case, it would be from an array of 3 to 4. Make sense?
Oh, that makes sense. Yeah.
So then 3 plus 4, 7 / 2. That means round down. So that's 3.5 rounded down to 3, 2, that which rounds down to 3, right? So yeah, then we'd only be looking at the element 3. So this works because we're always rounding down. So this is the tricky part about writing binary search, is the bounds, right? So sometimes people will say like use len of array instead of len array -1, but I was like, you know what, actually that's going to cause more issues than we want. And then, technically it doesn't really matter if you round down or round up, but also it does matter for some scenarios. So it's always safer to round down. because of exactly this kind of scenario that you're describing with like, hey, what if there's only one element? Okay, so yeah, this is the tricky part, and then yeah, the other part is tricky about what's in bounds to start with. So okay, so if we're looking for 4, we're looking at arrays from indices 0 to 4, evaluating index 2, it's not found, so then we call it from indexes 0 to 1. Wait a minute. What made a critical mistake here? Oh gosh. No. Oh my God, I can't believe I did this.
You're just printing the indices. That's fine.
Yes, no. I'm sorry. I confused myself because I was initially going to start this with len array, and then I changed the len array -1. So these bounds are inclusive, which actually means left and right, they're both inclusive. So actually, in this case, it's not the same thing as our slicing notation. It's just telling us the indices, every single index that's included. So if left is right, that means that we're just including element like 4, for example, if left and right are both 4. So actually, no, this should be -1. Does that make sense to people? Why? Because basically what we want to say is 3, 4, 5, right? So let's say left was equal to 2 and right was equal to 2. Well, that's just saying that we have 5. That's the only element we have if this is both left and right. Does this make sense? Because this is not the same as our slicing notation, because we're not being inclusive. Sorry, we're not being inclusive with slicing notation. We are being inclusive with this notation. Does this make sense? Yeah. It's a very simple fix. If we wanted to make a variety, like, if we are doing something where we're not inclusive of this right index the same way we aren't with our, slicing solution, we just have to change it to this. Okay. So Evan's condition was actually 100% right initially. Yeah, what he had, yes. Okay. Well, he said equals -1. I would just say less than equal to -1 to be safe, but yeah. And so if we start out with an empty array in this scenario, we'd be passing in 0 and -1, which already these bounds would be invalid based off of this. Any questions about that? Okay. So let's just ignore this though to make this less complicated. Okay. So if we do this, right, if we're looking for 8, right, we're looking from 0 to 4, including 4, right? We try looking at 2, not found, right? If we look for 3 to 4, we look at 3, not found. 4 to 4, look at 4, not found. 5 to 4, well, that doesn't make sense, so we terminate. Does this make sense to people, how this works? Let's hopefully it works for this. So 0 to 4, invalid index 2, not found. 3 to 4, validating index 3, not found. 4 to 4, 4, and it is at 4, so it finds the target 4. Does this make sense? Okay, cool. So we have binary search down, yes? Thumbs up. People can write this from scratch themselves. Okay. I see some nods, so I'm happy. Okay, cool. So how would people, make this interesting? Like, okay, it feels like, hey, binary search is just, that's it, right? Done. Well, we actually, for example, there's an interview question that our company uses that uses binary search, right, in the problem, right? It's not giving, too much information away just to say that it uses binary search. It's kind of obvious that it uses binary search. But the question is then, what is the sorting algorithm that you should use, right? Because in this case, we assume the array is sorted from left to right, like, in ascending order, right? But that's not the only way to sort numbers, right? Maybe you're sorting objects, and maybe you're sorting, like, for example, strings, not in alphabetical order, but based on length or something like that, right? And you're trying to find a string with a particular length. So what makes it interesting is basically, can you sort the initial array, based off of a way that makes sense to whatever object that you're looking for? And if the array is arranged, based off whatever sorting function you've specified, then like how do you narrow down the bounds based off that scenario? So if you order all these strings based off of length, and if you're looking for a string with a particular length, now you just have to change this line 13 to be like, hey, if the length of this string is not what I was looking for, if it's too small, go to the left. If it's too small, go to the right. If it's too large, go to the left, something like that. So that's basically where the trick lies, figuring out how should the array be sorted. So that's also something you can change in your sorting algorithm. It doesn't have to be sorted from least to greatest, right? In fact, for your homework yesterday, I said, hey, sort it from greatest to least, right? And then you do the same for like when you're finding an item. So we have like 5 minutes left. Do people have questions, or do we want to maybe walk through some of the homework from yesterday? You know what I'll do? I'll say, hey, just add one more problem to your homework. So instead of just being selection sort, well, no, yeah, we've said insertion sort on your homework. Okay, we said insertion sort. You guys understand insertion sort. Let me add selection sort here, but then let's solve that problem right now before class finishes. Okay. So the way selection sort worked, this was Jacob and I think Manisha's algorithm, right? They were like, hey, let's find the greatest element. Sorry, they were saying find the smallest element, and the second smallest, and the third smallest. What we want to do is find the largest element, then the second largest, then the third largest, right? So how do we do that for this algorithm?
Wait, are we allowed to use the max function?
You can use those functions if you need them, but I don't think you need them for selection sort, right?
Yeah.
You shouldn't need it, right? Because it's just comparing two items and swapping.
Yeah, okay.
Anyone have any ideas how I should start?
Set number to be negative, and then use a while loop. Use 0 to what's the thing? Length of array and length of ARR minus length of ARR. Yeah. But you can so say iteration. Okay, and then before that, set a number to be like -1 or something. So say let n be -1 prior to this loop. You can let n be -1 because you can. Nope.
Let's call this largest maybe, right? And largest index, we can also say is -1 or something like that, right?
Isn't it better to make the largest like the first element in the array just to be on the safer side?
Yeah, that's probably safer. That's a good idea, because then, so yesterday we were just assuming, and I said let's set it to -1 or none, and or something like that. I said let's set it to -1 because we can assume everything's positive just for the time being. But yeah, this is probably better design. Let's assume it's like this. So this way, even if there's negative elements,
And okay, and now have another loop. Another for loop.
right? We can say something like, actually, let's try this.
In range.
So we can say if element is greater than largest, then that should become the new largest, right? And
yeah,
would be right. So then at the end of this, we're left with the largest element and the largest index. Now what do we do?
Just return them.
Well, we don't want to return them, right? We need to swap.
Return largest. Oh, no, I'm sorry. You don't. This isn't a max thing.
Yeah.
Okay, so R of 1 and R of largest IDX you want to swap. So R of 1, R of 0, R of 0, R of 0.
Oh
Yeah,
wait, yeah.
okay, yeah.
This would actually be our iteration, right? And we should only be checking.
Yeah.
Oh gosh, this gets a little confusing. Let's try this. Let's do this. Range of iteration. Because we don't want to basically be going over the elements we've already sorted, right? The first n elements or first iteration elements. Does that make sense to people? And apologies, like Evan,
Now
your mic is cutting in and out, so I may have said the correct thing and I may have been writing it incorrectly, but yeah.
Okay, so now you can swap the two. So say equals ARR of.
Nice. Okay. So did this make sense to people? And would you agree? Yes, anyone? Anyone? That didn't do anything. Hold on. What's going on here?
Someone's not zooming.
Are we sorting in ascending instead, or something like that?
I don't know. What's going on? Let's go to an 8 here. I didn't do anything. What? Anyone? Why is it not working?
Become a citizen. You have to debate whether or not you understand that Israel is a Jewish state. And you have the right to exist.
Then go to Germany.
What's going on here is we start off by saying, okay, whatever, like, okay, so iteration is basically the number of like, okay, right now we're going to get the 0th element correct, right? If iteration is 0, we want to get the 0th element correct. If iteration is 1, we want to get the first element correct. If iteration is 2, we want to get the second element correct, right? And so then we take all the elements that are from index iteration to the end of the array. And then we basically try to figure out what's the largest amongst those, right? That's what this section is doing. Find the index of the largest one, and we swap that with the iteration, right? Does that make sense? How we're swapping it until we get the largest one and second. Okay, cool. So you have to do exactly this sort of thing: bubble sort, insertion sort, merge sort for your homework, and then the rest of these should be pretty simple. And hopefully, now that we have more recursion practice, you guys can do these as well. Okay, it's a little over time. Sorry about that. Yeah, we'll stop the meeting for today, and I'll see you all tomorrow.
Wait, so for the homework, do we just have to finish like yesterday's thing? Okay, so we don't have any new thing.
No.
Okay. Okay, thank you. Have a good day.